Lab Guy here. Let's take another look at the video sync generator, but this time let's look at it on my digital oscilloscope. 4 channels, 1 gigahertz of sampling. Ooh, what does it mean? I don't know. So let's get on with it. Let's look at our signals on the digital oscilloscope. This is a screenshot of my Tektronix TDS-744A 4-channel digital oscilloscope. We are looking at the paused display of 4 of the signal outputs from the television sync generator. Before we begin, I want to explain that the picture looks washed out on this CRT because the monitor has developed a problem of its own where the black level, this should be black, the black level has jumped up. I have a rule of not opening up my test equipment if I absolutely do not have to. As you can see, the oscilloscope is fully operational, albeit with this slightly washed out image. If I were to open the scope and begin messing with that, I'm fairly certain that I could render this scope dead as a doornail before I was done. So in light of that, or until I can get an LCD conversion kit for this scope, I'm going to live with this problem. I paid $2,000 for this oscilloscope about 7 years ago. Since then, it has been in the shop twice and has cost me $1,200 one time and $2,000 the second time to get it repaired. I will not put another penny in repairing this oscilloscope. I will convert it to an LCD monitor if I can find one of those kits, but this product is really out of date now and accessories and such are hard to find. One other caveat about this particular scope: Tektronix is great about putting television trigger in all of their oscilloscopes. For whatever unknown reason in the universe, for this oscilloscope, television trigger was an option. And this particular scope does not have that option. If you happen to have one of those option boards lying about and would like to part with it, let me know. However, this scope cannot trigger on television signals directly, but as you can see, that's not a showstopper for old Lab Guy. So now, let's get on with the show. Let's begin by pointing out what we are looking at. We are looking at 4 of the output signals of the Fairchild F3262A sync generator IC. Trace number 1 is vertical drive. We are currently looking at the vertical interval of the signals. Vertical drive is a pulse in the television camera that generally drives the scan circuit, the vertical scan circuit or frame circuit, whatever your preference. Trace number 2 is composite synchronization. This composite means that it is composed, or a composition of, several different pulses. There's horizontal sync pulses, there's the vertical sync pulse, there are equalizer pulses, and there are serration pulses. That's a set of 5 different pulses combined together to create a composite sync signal. In the last video, I didn't go into any depth of why we have these little double speed sync pulses in here, but in early televisions, the sync separator consisted of, let me be specific, the vertical sync separator consisted of an RC network of components that was sensitive to the low frequency aspect of the vertical sync pulse. Because it was AC coupled, when this vertical sync pulse starts, the signal would jag up, actually would jag down, jag up, and jag down because it's floating across the capacitor, which could then mess up the ability of the sync separator to find the sync pulse or to trigger as this thing bobbed up and down to cause the picture to bobble up and down and jump. So these pulses were put in the earliest days of electronic television to take care of equalizing the vertical sync pulse detecting circuit. That is their function. Today, with modern circuitry, and basically since the late 50s, these pulses weren't absolutely necessary, but they were put on the broadcaster to provide them to make the home television receiver affordable. This was a cost-reducing function for the consumer. So moving on, composite sync. Down here is composite blanking. The big low cycle here is vertical blanking. This is the signal that turns off the beam in the television CRT during the vertical reset time when the beam of the television has reached the bottom of the screen, has been triggered by the sync to return to the top. The magnetic field in the deflection coil must reverse, and because of inductance this takes time. And in early TVs this was extremely difficult. So they provided 21.5 lines of time for that vertical scan circuit to reset to the top and begin scanning down again before they turn the video signal back on. In color television, we have what's called the color burst. The color signals are riding on a 3.5 megahertz subcarrier, and it is phase modulated. To demodulate phase modulation, you need a reference pulse. This is called the burst, and it sits on the back porch of horizontal sync pulses, and it's 8 to 10 cycles of 3.58 megahertz at a locked phase that is sampled by this pulse. This is called the burst gate, and it tells the color oscillator that right now, at this point, when this little pulse goes low, to look at that burst and lock your crystal to it. It does it every television line. During the vertical sync, there are no bursts. So there are no burst flags in here because the color oscillator would be sampling noise, and it would cause the color oscillator to jump out of phase and then take several pulses to recover, and you could have little rainbows at the top of your picture. So those are the 4 pulses that we're displaying right now out of 8 potential signals on the output of the 3262A sync generator. The scope is currently in pause. It is not running. The reason for that is that in interlaced television, the pulses are different in the 2 fields. So let me put this into run. Alright, now you can see the trigger phase of the scope, which is triggered on this point in vertical drive. You'll see that what appears to be these lines jumping half a line, they're not. These are actually steady. This edge in one field falls evenly on a horizontal sync pulse, and in the next field drops halfway between those fields. So in other words, from this edge to the next edge is 262.5 lines. So in one field it falls on a sync pulse, and in the next field it falls halfway between 2 sync pulses. This is how they achieve interlace. The horizontal sync is a perpetual continuous stream of 15 3/4 kilocycle pulses, approximately. In PAL or NTSC, it's approximately that much, and it's a continuous stream. The point where the vertical sync falls, and that applies to this edge as well, or the vertical drive, in one field is, we'll call it even, and in the next field, odd. It falls with the horizontal sync, and in the next field it falls halfway between the horizontal syncs. Enough said, and you'll note that these are jumping. The horizontal here is actually stable, but because we're triggering on this trigger that in one field is on an even pulse, and in the next on it halfway between them, it makes these look like they're moving because of the nature of the trigger of the scope. This is a stroboscopic effect. Now, that is the vertical interval of the video signals. Looking at the vertical interval, I've changed the bottom two traces to the two field pulses, odd field on the first on this trace and even field on this trace. Now, because again of stroboscopic triggering, we're alternatingly seeing one or the other. So let's reduce the time scale. The nice thing with a digital scope is you can do this without flicker. On an analog oscilloscope, this would be flickering. Now I'm going to change the trigger to one of the field pulses to make this thing stop being stupid. There we go. So we're triggering on the odd field pulse. So when this pulse is high in the vertical sync, it's an odd field. When this pulse is high, it indicates an even field. So these two pulses are available from the sync generator, and generally where you would use these is in the case where you would be doing a three-dimension system where you are doing field sequential left and right. That's one use for such a pulse. I can't name any other useful function for the pulses, but it is provided unless you want to specifically trigger your oscilloscope on these. So this is vertical drive, composite sync, which is being massively undersampled because of the low scanning rate, odd field pulse, even field pulse for completeness. Now let's move on to the horizontal signals and look at them, and we will be returning to the two original composite blanking and the burst flag signals here. Now we are looking at horizontal signals. First thing I'd like to comment is you see the flashing on the composite blanking and the composite sync and the composite blanking. What you're seeing is that on every few dozen scans of the scope, the vertical interval is passing through, and that's what that jumping is. It's decided to behave itself now, but there's no particular reason why it should. So we're looking at horizontal drive to horizontal drive, horizontal sync, horizontal blanking, and color burst flag. All right, so let's expand so that we can see these in greater detail. Okay, that's too much, and that's good enough, and we will hit stop. There we go. Now we've frozen the sampling on the digital oscilloscope, another great feature of a digital oscilloscope. For fast phenomenon, you can trigger in a way to grab an image and stop it. So let's look at our four signals. Again, horizontal drive, which would drive your horizontal deflection circuit specifically. It says right here, boom, it says start the next horizontal scan. And so at this point, your horizontal scanning circuit would be over here, and it's doing its retrace thing now during the blanking interval. Just like the vertical, it takes time to go from the right side back to the left side, so we turn off the beam. You'll note that the falling edge of drive and the falling edge of blanking line up. We'll turn the beam off and tell it to reset. So while it's resetting, we now have the output video coming out has been blanked. So the signal coming from the tube, from the camera sensor, is turned off. So the video output is a black line. It's a straight line through this interval. So at this point we wait 1.5 microseconds and insert the sync pulse. Now this is the pulse that is added to composite video. We're making a composition of a sync pulse, a blanking pulse, and active video, which would be added in after the blanking is over. Active video would be out here. So if it's a color camera, then a fourth function occurs. At this time on the back porch following the sync, there will be a color burst right here, and this pulse says open the gate and feed a piece of color signal here that is unmodulated, and it gives us a reference of phase. All of the color bursts are all in exactly the same phase, and in fact they're relative to their phase to this falling edge, they're 57 degrees. I don't even care why. We just know that they're at a fixed phase for our color oscillator in a color television to synchronize to that burst. So essentially in the blanking interval, you have a horizontal sync and a color sync. Color sync for demodulating phase modulated color television. So this is essentially the construction of the horizontal interval inside a television camera. We have a sync pulse specifically for the camera's horizontal scanning circuit. We have a sync pulse which is added to the video that is sent to the television or tape recorder or switcher, whatever downstream that needs to synchronize. We have a blanking control to turn off the analog part of the video signal of the camera tube before we add this signal in. And then we have another gating signal. These are called gates. That it tells the color circuit right now, give us a color burst. Okay, that is how the horizontal interval works in a color television signal. Now again, the blinking here is because vertical is passing through this time period. So we'll slow the scan down so we can see multiple television lines and try to capture a vertical interval. We'll try. There we go. There's the start of vertical in the blanking. We're not looking at enough TV lines. So it's like fishing. One must be patient. At any rate, you can see the vertical components passing through as a result of the sampling rate of the oscilloscope. If we slow down enough, you can see this is what we're seeing. We're seeing that vertical component walking through. Sometimes when you look at your oscilloscope, you see things and you don't understand what they are. Well, that's what happens when you have two pulse trains that contain a high frequency and a low frequency. So as we speed up our sampling to look at our pulses larger and larger, you will see that walking through. And there you go. Those are the essential pulses coming out of the color sync generator. Now, one last thing. Let's take channel 3, which is composite blanking, and move it over and have a look at the color subcarrier itself that is produced by this chip as well. Alrighty then. Go to channel 3, and we want the vertical menu, and we want to look at this in AC mode, not DC. Okay, and we'll kick it up. The reason it looks aliased is because we are looking at a frequency range of 15 kilohertz, and this is 3.5 million cycles. So it's going way faster than our sampling. So let's change our trigger to channel 3. Channel 3. There we go. And dial it in. And we're now triggered on subcarrier. And we can see our 3.58 megahertz subcarrier. And turn off all these menus because they're confusing. Alright, you see our other pulses flashing through because we're triggered on a wildly different signal. Now, let's use our cursors to measure. We'll bring up some cursors. We want vertical bars. Now, one of them's here and one of them's here. So let's move the one over, and we'll put it right on the tip of that sine wave, right there, right by the center line. We then select the other one and bring it over and put it on the very tip of this wave, and then we can read the time period. I can turn off the menus here, and we can also say measure. We want to measure frequency on channel 3, and we can turn this off again. So over here it's telling us that the frequency of channel 3, this wave, is 3.579. Every once in a while it says 579. 358. With this measuring technique, if you get 3 digits of accuracy, you're doing well. So it says it's 280 nanoseconds, 3.58 megahertz. That's our color signal. And now we can go back to measure, and we want to turn off, we want to remove measurement. That's down here. Remove the measurement, because these things actually, let's go measurement 3 and say remove measurement. Oh, come on. Turn off the menu. Okay, measure. Select measurement for channel 3. Remove measurement. And measurement 3. I don't know why it isn't turning it off. How about all measurements? There we go. Turn off this menu because it's very confusing. Move our trigger back to channel 1. Adjust the trigger level, and then turn down our sampling speed to something realistic so we can see our pulses. And there you go. We're back to where we were. Now, here's the color. Here's the color burst flag, and it tells our camera at this moment, take some of this sine wave and put it on this signal, and now the television has a color sync pulse. Well, boy howdy, wasn't that fun. So there was the signals we looked at yesterday, but this time we could see 4 of them at a time, and we could do extra tricks using the features of the digital oscilloscope. Note that I didn't bother trying to use any kind of delayed sweep techniques, as the digital scope has the ability to present a flashing image as a steady image, because it's stored in memory and is being shown to you as a computer graphic, essentially. So we looked at the 8 signals of the Fairchild 3262A chip, which was vertical drive, horizontal drive, composite sync, composite blanking, burst flag, and field 1 and field 2 pulses. with that zoo of pulses, you can build a video signal generator, a video game, a television camera, either black and white or color, and so on. So a very useful chip. These are available from Voyager Components, not Voyager Electronics. I said in the last video, Voyager Components on eBay. One word, Voyager Components. You can get yourself a 3262A. You will also need a 74LS00 or a 74HC00 chip and a 14.31818 megahertz crystal oscillator. And with those three parts, you can put together a sync generator for your video project, and it gives you 8 essential signals ready to use. The work is done for you in 3 devices. Very simple. You can go to my website, labguysworld.com, click through to the electronics projects, and look at either the Chief or the Tiny Ike camera projects, and both of those projects have a page devoted to this sync generator with information on where to buy them. They're reasonably priced at $14 a piece, and they are available from Voyager Components. This is an unpaid plug. So thank you for watching my videos again, and I hope you got something new out of this one. You can see that you may not want to sink a lot of money into a super fancy oscilloscope simply because it's like owning an Italian race car. Yeah, it's great. It makes your friends go ooh and ah, and when it breaks, it costs a fortune to get it fixed unless you are the kind who wants to wrench on it yourself. And really, when you're done, is it really right? So anyways, those are my conclusions for this video. Have a nice day, and until next time, Lab Guy out.